PhD at Israel, and then he went to Indiana Bloomington to do his postdoc with gene transfer. And Ami is very good at computation and modeling and all of this stuff, so he will introduce some of the related works. So let's welcome Ami Eidels.
Thank you very much. Before I start, I should try and say this.
That's not traditional.
So I will try and give you an appetizer. And I will explain it what I mean. So thank you very much for the kind introduction. And also I have to say thank you on behalf of myself, Daniel, Andrew, and Matt. We had the most wonderful time here. We feel very lucky to be hosted here so kindly and nicely and generously. And I think we also envy you a little bit. We think that you are very lucky to live in such a wonderful country and have such good food. Also, I would like to extend my thanks to all the people that have helped us, obviously to Jessica, thank you very much, to Shulan, Poppy, with Alex, Professor Young, and Professor Tom, as well. Sorry, Professor Wong, so thank you very much, and Shulan. I think really we had a terrific time, and I simply don't have any words to describe it. So thank you very much. So when I say that I would like to give you a bit of an appetizer, what I really mean is that this is rather late now, and I know that at this time of the day, after 2 long days of a workshop, it is already very, very hard to take new terms in. So I will try to change gears and slow down a little bit. And really by the kind trend, what I would only try to do is not to fool you, to give you a full description of the kind of things that I do, but just a bit of a taste, in the hope that some of you would find this interesting enough and would later on contact me or be in contact with our research group for further development. So I don't expect to cover everything in 1 hour. There are some codes available, but I will not go over them right now. So I will do this a no computer code lecture. You probably most other lectures, so you don't need to do the codes. But just that you will know, we will be hosting a complete SFT website on NewCA. So that is the Newcastle Cognition Lab website that Andrew had started before he had departed to Tasmania. And this particular website will have a bunch of codes and to help people use different measures that we use. Some codes are already available on my own website, which is also newcl.org. And if you just click on some of those NetHub files, you can see that those codes have documentation, so they have explanation of what you need to do in order to organize your data and so on. And sometimes it is easy enough to use it if you are used to work with MATLAB, and if not, you can email me and I can help you set it up.
So maybe later we can go to the websites.
Yes. Sure, certainly. But certainly I do not want to go over these codes right now. So I will shut this down and I will really give you a more standard presentation, I think, in the hope that it will make you interested enough, that it will start your appetite for this kind of work. So Andrew I should say particularly Andrew talked a lot about the LBA model, how to use it, how it can be helpful, and different methods of using the LBA model. Now, the LBA model was initially set up to assist with very simple decisions. And simple decisions could be which flavor of ice cream should I eat today, banana or chocolate? And for the LBA, there may be one accumulator that says chocolate, another one that says banana, and whichever wins, that's the ice cream that you buy. Sorry, I also should say, I apologize in advance, I'm from Israel originally. I was not born in Australia, although I'm currently in Newcastle. So my English is, and so I will try to speak a bit slowly to not commit any mistakes. If I'm committing mistakes, don't tell me. It's too late for me. So we can in fact use the LBA not just for the very same purposes that Andrew had showed us, but also as a kind of a clever measurement tool. So sometimes when we measure data, we look at mean response times in condition 1 versus condition 2, or in the accuracy rate of condition 1 and condition 2. The LBA model can be used not just to tell us something profound, something clever about how the cognitive system operates, to some extent it can be just a very clever measurement tool. We can use the parameters of the LBA model not just to tell us about latent variables, but also just to tell us which process is done better or faster. And that is what I will show. In particular, I'll show you how we use the LBA to measure capacity. How do you say capacity in Chinese? Longlian. So before I start, I need to ask two very important questions. First of all, is capacity really important? Important enough for you to listen and work your brain hard? And two, do you really need to be math experts in order to measure capacity? With the first one, I would say capacity is really important. And to explain why it is important, I need to tell you a short story, but I will probably need some help with Chinese. We'll see how we go. Let me know if this makes sense or not. So my good friend Daniel here is renovating his kitchen. He's doing a new kitchen in the apartment. And he, hypothetically, that is only a story, of course. And so he called a builder, a person that knows how to renovate the kitchens, and he told him, I have this kitchen, how long would it take you to fix my kitchen, to make the kitchen new? And the builder says, 2 weeks. So Daniel consulted with his wife. Have you met Kate, his wife? Yes? And they thought, oh no, 2 weeks is too much time, because you cannot live in an apartment where you do not have kitchen. In Taiwan you can. In Taiwan you can. But in Melbourne, the food in the street, the market, in Australia is not. Well, sorry. It's very good, but not meeting the. So Dan knows that it takes this builder 2 weeks to renovate the kitchen. And he thinks about this and agrees that he cannot wait 2 weeks. It's too much to eat in the street. He's only willing to wait 1 week. But the builder cannot work that fast. So what does he need to do? He needs to perhaps get not only but one, but more builders. And in this particular example, maybe 2 builders. So he calls the builder and he tells him, can you bring more builders? So the work will be accomplished more quickly. And the builder said, sure, my brother can come. And so they both come in, and Dan needs to eat outside of the kitchen. And 1 week had passed, and the kitchen is not ready. And when Dan asks the builder over the phone, you promised me that you would bring another person. 2 people, you should have finished this in 1 week. The builder says, I only had 1 set of tools to share with my brother. And that's quite important. Do you need to translate this or? So this is really important. And the reason this is really important is that the brain, to some extent, is like our set of tools. If we like to do many things at the same time, but we only have one set of tools, or a limited set of tools, then we cannot accomplish all those things together very well. Does that make sense to everybody? Yes. Okay. That exactly is the idea of capacity. Capacity is how much force, how much resources the brain has. Do we have enough to divide it to many things at the same time? Or is it only one set of tools such that I can do one thing maybe, and then another, and then another, and then another? So that is the issue of capacity, the cognitive ability to allocate resources, to process information. So I hope that you trust me now that capacity is important, because even if you have 1,000 builders and only one set of tools, you won't be efficient. And the answer to this is yes. The second question is just as important when I'm coming to measure the brain's capacity. And that is, to calculate those models and sophisticated measures of performance, do I need to be a math expert? Or is there another way to go? And the answer to this question, luckily, is no. Now, that doesn't mean that it's not a good idea to study mathematics. As Cam can testify, this is a really precious property, and in fact, the single best thing that you can probably do as students is to get more math. I did not have early math education. I only studied math when I went to Indiana, and that is rather late. The brain is, my brain was already old, and I'm sure that I didn't do as well as some younger students, right? But nevertheless, I think the important point is that even if you're not a math expert, you can still do quite well, thanks to, one, computer programs. Nowadays, we can tell the computers to do things that 50 years ago, we had to solve with a pencil and paper. So that is really good. But that's not enough. The other good thing is that we have some really nice people. And those really nice people have been kind enough to write computer codes or come up with clever mathematical ideas that we can implement. So, Andrew Heathcote and Scott Brown in Newcastle came up with the MBA model, but they did not just develop the model for the first time. They continued to run those workshops and educate people on how to use it. So that's very important. This is when it comes to the MBA model. I will talk to you about another measure of performance, the capacity coefficient. And those two people have been quite fundamental. Jim Townsend from Indiana had done all the proofs. So he sat down one day, or for many years actually, for a period of 20 years, and he proved everything that we need. And once he proved it, he published a paper, and once the paper is out, we no longer need to prove it over and over again. That's what happened. And John Hupt from Ohio is taking this one step further, and he is now writing computer codes that allow us to implement those mathematical proofs. So instead of each and every one of us writing the mathematical equations, Jim proved it, Joe writes the computer code, we can use it relatively easily, and so we can calculate rather complicated things today that had not been possible 20 years ago due to those very nice So what is capacity then? We have to be a bit careful, because in psychology, people use capacity for very different purposes. For example, one important use of capacity is in working memory. When people talk about working memory capacity, the question is, how many items can you keep in your working memory? And sometimes people talk about magic number, 7 plus minus 2. That is not the capacity that I'm talking about. That is a different concept. The capacity that I'm talking about is how well we can cope with many sources of information. So as we need to do more and more things, how well we can do this. One example that I like to give is this hypothetical example, assuming that you are aviators, pilot of an aircraft. And if you are a pilot in an aircraft, there is a warning system against low altitude, so that you won't run into the ground. Now that warning system is both a visual signal and a beep sound. I don't know if the volume is set up here, so let me put this in. And that's true. Obviously, this sound is not the real sound, but this notion of presenting both auditory and visual warning signals is very common in all aircrafts. And in fact, in warcrafts, there's also tactile vibrations, so your throttle would vibrate to give you an even extra source of information. So engineers tend to think that the more things you show a person, light, sound, vibration, the better it is. But at least from a theoretical perspective, it is possible that you cannot deal with it, right? If the brain only has one set of tools, maybe throwing too many things can be harmful rather than helpful. So what we do is we develop ways to measure capacity. We develop ways to measure how people and whether people can effectively cope with lots of sources of information. So that is what I will try to do. I'm aware of the time, and so I will not cover everything. I will try to talk a little bit about SFT, but I may skip through this relatively quickly because we have a local expert. I will then talk about how we use the LBA model to measure capacity. So that is the sophisticated way of measuring capacity using the LBA, right? How we can use a model to tell us about rates. And then I will show you some example data. If time permits, I would actually like to also talk a little bit about another set of data from the aging. And I know there is some interest in aging here, so I might actually skip some of this to more quickly go to the aging area. Before we talk about the math and the method, we need to understand how the data is coming to calculate capacity. And the data is coming from a task that is called the redundant target detection task. If you are a participant, what I ask you to do is this. Do you or do you not detect a bright dot on the next slide? If you see a bright dot, then you press one key. If you don't see it, you press another. Okay? 2 dots? Yes. There is at least 1 dot, so I need to press the yes key. That's the correct response. Again, the same question, and that is another trial. You see a bright dot in the next slide. This time there is only 1 dot. And again, the answer is yes. The important bit here, and you can already guess what is going to happen, we have now a condition with only 1 source of information, 1 dot. Earlier on, I had 2 sources of information. So I can compare how well does the brain process 2 items versus just 1. And this will give me some measure of processing capacity. Does that make sense?
Yes.
Absolutely. So we have some of these as well. I will give you an example. Sorry. So another trial, no dot appears. So in this case, you need to say no. But you're absolutely right that the design has all the combinations. So what I've showed to you was a set of example trials, and you can, on each and every trial, either see 2 dots, 1 dot on one side, 1 dot on the other side, perhaps no dots at all. So we have 4 conditions in this design. These are called the single target conditions, and this is called the redundant or double target condition. And really everything that I will show to you next is about comparing this to these two. It's really important that you remember how the design is. We run this task many times. Each time that you see a dot, you press a key, and I measure the response time the same way that Andrew collects response times for the MBA analysis. And then I collect response times across those 4 trials, 4 conditions. And for each and every one of these conditions, I can estimate or calculate a number of important distributions. So Andrew and Dan already mentioned the PDF or probability density function. Yes. Probability density function. The integral or the cumulative. And the complement of it is the survival function, which Andrew also used earlier on. So the survival function is called a survival function because it tells you the likelihood that the process had survived, had not finished yet. These are telling you the probability that something is still happening. Sorry, that something finished. This is telling you the probability that something had already, sorry. This finished, not finished, survived. Survival function?
Survival function 是那个一减去累进几率函数，所以累进几率函数就是说到这个时间点你已经完成了多少东西。那反过来的话，就是说最下面就是说到这个时间点还有多少东西还没有完成。
And from the survival function, you can calculate almost what we need. There is another small step that is called the hazard function. The hazard function tells us the likelihood or probability of a process to happen in the next instant, given that it did not happen yet. It's a bit of a confusing term, so I will give you an example. Suppose that you are in a bus station and you are waiting for the bus to come. And you'd like to know, is the bus going to come now? No. Is the bus going to come now? No. Is the bus going to come now? The hazard function tells you the probability that the bus is going to arrive in the next instant, given that it did not arrive yet. It's called hazard because it is often used in engineering to calculate the instantaneous risk or hazard of, say, bridges to collapse. So, if you're an engineer, and I understand that MCKU is very good in engineering,
yes.
If you're an engineer and you are going to inspect a bridge, you'd like to know what is the risk that this bridge would fall down tomorrow, next year, and so on. That's what the hazard function is telling you. What is the likelihood that this bridge will collapse, given that it has been standing so far, given that it had survived so far? You don't need to calculate this by hand. As I reminded you, these computer codes, they do all that. They calculate survival functions and do some other things. So once we've calculated our hazard functions, we get that bottom equation. That's quite important. This equation is the capacity coefficient. This is our measure of capacity. how good, how well does the brain deal with two sources of information as opposed to just one. Here at the top, that is a hazard function or a kind of hazard function with two sources of information, A and B, so two dots. And here at the bottom, that's one dot and that's another dot, where they are presented separately, only one dot at a time. So this coefficient or this function tells us how well we do with two dots as opposed to just one. Now going back to the question of capacity, if the brain has unlimited capacity, if I can do as much processing as I would like, then adding more dots compared with single dots does not hurt me at all. And this function will give us a value of 1. If on the other hand, when I have multiple sources of information, many dots, 2 dots, 3 dots, 4 dots, and more, my brain is shouting for help because it can no longer recruit enough resources, then here I will not do so well. If this part is small, this part remains the same, this entire expression is smaller than 1, limited capacity. And in theory, the opposite could also happen, but we'll skip this for now. Just remember, 1 means that you can do just as well when more and more information is coming in. You don't suffer. Less than 1 means that you have limited capacity. The more information you get, you start to suffer. You don't process information effectively. I'll skip a few slides that are not so important. Over the last few years, we have used the capacity coefficient quite extensively, and we have found it a very useful tool. We also found that in some cases, there are some limitations that we won't discuss right now. And so to overcome some of these limitations, what we will do is we will use also the LBA model to calculate a measure of capacity. So we really have 2 measures of capacity. One, the formula that I've just shown you. That is one way to measure capacity. You just take your data, you calculate some value functions and hazard functions, you put them in here, and you compare it to 1. The other one makes use of Andrews and Scott's LBA model to overcome some of the limitations of this function, which is still very useful. So the way it works builds up a lot on what Andrew had said before. I will only recap perhaps the important things for the capacity calculation, because I know these have been very long 2 days, and what happened yesterday looks already like last year, for me at least. So that's the LBA model. You know that the LBA model accumulates information in a linear and ballistic way until it reaches a threshold. You know that response time is the time that it takes for evidence to accumulate, plus some additional time that we call TER, which is the time for encoding and response. I often call it base time. So TER is a parameter in the model. Now, the parameters that I would focus on, or the parameter that would be of most interest to us, is the drift rate. There are some other parameters, but I will not concern with them right now. So remember the drift rate. The drift rate is how quickly evidence is accumulated towards one response or another. Now remember that I like ice cream very much. So I go to the ice cream store. We had a very nice ice cream the other day. Mango, I think. So maybe I have mango and guava ice cream. Guava ice cream. And so if I'm not quite sure which one of them I would like to order, then perhaps there is an LBA competition. One accumulator for mango and the other one for guava. But perhaps because I love guava so much, the rate of the guava is much faster. And that accumulator will win. We can use this rate to also learn about capacity. I'll show you in just a moment. Now, the work that Andrew and Scott have done allowed them to use the LBA model to account for decisions between, say, two alternatives, such as my mango and guava ice cream. But because of the mathematical properties of the model, you can in fact extend it to more complex decisions. And that is some work that Scott, Andrew, and myself have done with Chris Donkin is now also in Australia. And a lot of the analysis that I will show you really is his work, as well as some rather ingenious ideas. He's in the University of New South Wales. So suppose that instead of just two accumulators, guava, mango, I now also have chocolate, vanilla. The diffusion model found this a bit hard, but the FBA model can do this rather easily. Now let's take this to the redundant target effect. And let's try to see how the FBA model can describe the decisions in a detection of two dots. So I have two dots, one here and one here. To account for what happens in the cognitive system in the brain, I can say that there are two accumulators for one dot and two accumulators for the other dot. For the first dot, on the left-hand side, there is an accumulator that says, yes, the dot is there, and another accumulator that says, no, the dot is not there. Because in order to make a decision, I need to be able to account for the presence as well as for the absence of a property. So the convention that I will use is A means dot A is in place, and minus A, or the squiggly line, that means not there. So yes, the dot is there, no, that dot is not there. And likewise for the dot on the other side. Yes, it is there, no, it is not there. So you can imagine that if I now have two dots, if really what I see now is two bright dots, then for the left dot, this accumulator should have a higher rate than this one. Because the dot is there, it correctly identifies that the dot is there. And likewise for the left, very bright and salient and nice dot, this accumulator would have a higher rate than this one. Scott, I think, had written down the formula for what it takes for the model to solve a redundant target task. One way to think about this is that if your task is to say, do I see at least one dot? So if you see one dot on the left side, sorry, on the right side, another dot on the left side, or two dots, any one of these, go to one key. If you don't see anything, you press another key. That formula describes this decision. So this is just a mathematical way of saying what is the likelihood or the probability function of responding no, there was no dot. If you think about this, to provide a negative response, in order to say no, for me to say there was no dot at all, I'm sure there was no dot, these two accumulators, the not A and not B must win the race. They must win the race because if any of these reaches thresholds first, I will say, oh yes, I see a dot. And because I'm interested now in the probability of saying no, no dot, these two must win. And that likelihood function captures that relationship. Essentially what it tells us is, well, I would like channels A and B to not finish. That's the survival function. So survival function is the probability that the process is not finished. So A and B are not finished, while not A, not B are finished. And likewise, we can write the equation for the yes response. There are only two responses in this experiment. Yes, I see one dot here, or two dots, all goes to monkey. And no, I see no dots. Now, we can connect the LDA back to capacity. The important parameter that we are after is the rate of evidence accumulation. V.
所以他要做的作业其实很简单，就是你要看题目上有2个点，或者是有1个点，或者是没有点。那如果有任何一个点出现，你就按1个键；那如果都没有点出现，你就按另外1个键。所以刚刚的那个 likelihood function 指的，所以它就假设有4个 accumulators。那这4个 accumulators 就是分别是左边的有 target 出现。然后左边的没有 target 出现，跟右边的点有 target 出现，跟右边的没有 target 出现，所以总共有4个 accumulators 分别去竞争。那谁跑到终点，谁就赢了嘛。那所以刚刚在算的一个 likelihood 就是说，你要回答没有出现的那个几率会是什么？那个没有出现的几率就是两边同时都没有发现有点的几率乘以那个左边没有点跟右边没有点的机会，这3个乘起来之后，就是你会回答没有看到点的机会。所以其实它的那个概率的likelihood function 其实就是在描述这些几率的关系，这4个 accumulators 之间几率的关系。那一样的道理，你可以去算，你会回答 yes， 就是有发现有点的出现的。likelihood function 那就表现在这边。那其实不用觉得它太难，其实我们只是把那个很复杂的中文，然后用比较简单的数学把它表现出来。那接下来就是我们要去optimize 这些 likelihood function， 然后找到它的参数。看这样。
This is also a good time for questions. 有没有问题？ That is a very good question. I perhaps should reiterate it now because when we run those experiments, we actually find that those effects are very yes. So, Dr. Shran asks, what if the dot appears on this side and I need to press yes on this key? Or if the dot appears here and I press yes, wouldn't there be a difference? And the answer is yes. There is a preference. We are faster and better if the response end is where the stimulus appears as opposed to the opposite direction. This is called the Simon effect, and it turns out that it's quite a substantial effect. To overcome this problem, I have to say, we typically don't present dots on the left and on the right, but rather like that. So in actual experiments, the real data that I will show to you is like that. However, early studies in the 90s were not aware of this. Well, they knew the effect. They didn't know that the effect is so big and wipes out everything else. Now we are quite able to do vertical presentation. Alright. So I think this is the really important bit. This explains how we measure the capacity of the system using the LBA. So we have those LBA accumulators. We can estimate the rate of processing. What is most important is that we can estimate the rate of processing each one of the blocks. In the double target condition and in the single target condition. In other words, I can measure how efficiently you process this dot when it is alone, that's the single target, versus how efficiently you process this dot when there are two dots. That's the double target. Chengta, that's a bit tricky, so maybe I will reiterate this and then you can translate perhaps. Alright? So the big question is this of capacity. Are we as good with one dot as we are with two? Are we better with one dot as we are with two? Are we better with two dots than we are with one? And the way we test this is by looking at the LBA processing rate. I did not say this earlier, but remember that the model, the LBA model, is not just mean response time. It also takes into account the accuracy, the error rate, and the entire distribution. That is why this exercise of comparing them is very different to just comparing mean response time to single target and mean response time to double target. This is not just where am I faster, this is where is my processing more efficient. Is it more efficient? Sorry. How well or what is the processing rate of a target, a dot, when it is alone, versus how quickly or how efficiently I can process that dot when there is another dot. If they are equal, if those two rates are the same, that means that I can do one or two dots equally well. And that is what we call unlimited capacity. The brain can do as well with two dots as it can do with one. I know that's a bit tricky. Chengta, can you help me here?
所以他在这边就是他去用 LBA model 去估计那个不同的 accumulators 的 distance。那你可以去想象，就是说 given 两个点跟 given 一个点的时候，我们可以去算它讯息累积的速度。那如果说你发现两个点就是它 DP 的状况 ，double target 的状况，如果两个点的状况跟一个点的状况，它讯息累积的速度是一样的时候，也就是说它不会受到你多增加了一个点的讯息，然后去改变它的处理速度。那我们这边就把它称作叫做 augmented capacity。那如果说你增加了一个 information， 就是增加了 information， 增加了一个点之后，你反而让你的速度变慢了。那我们这就是说，因为你的容量是有限制的，因为我同时叫你做很多事，可是你是有限制的容量，你没有办法同时处理这么多，所以你就变成 limit capacity。那如果说你反而变得更好，那这个就叫做 super capacity。
So really, that is the important bit. Soon I will show you the values of VDT, that is the rate of double target. So DT, that's two targets. ST, that's single targets. I will show you that from real data, and we'll see how they compare. You don't need this. I will very quickly summarize them. We think that capacity is really, really important. Why? Because, well, if you don't take capacity into account, you will end up eating in the streets 1 extra week. So we can calculate capacity either using the capacity coefficient or a related measure that is doing something very similar, that compares, just like this one, compares two targets versus one, but does this using the LDA. And those two measures, they tell us exactly the same thing, or should tell us exactly the same thing. They may complement one another. CT of 1 is unlimited capacity. Chemka had done a lot of work about the capacity, and sometimes capacity is limited and sometimes it is unlimited, and he has a lot of work on this. But we can also get to the conclusion of unlimited capacity by examining the rates. And the rates of the LBA model help us to overcome some limitations that we may encounter here. So together, this is a rather useful strategy to use. So I will show you some data, but I know it's very hard, and I know this is the end of the workshop, so maybe for just 1 minute, stand up and stretch. Can you do that? It's quite good. Yes, please. No, 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 no. Yes, so I think I missed this. I think that in order to get to the aging data, I will skip the first experiment. I will just give you a very brief and advertise there so that you will know that this exists, and that so if you want to ask me about this, we can. This is concerned with configural processes. That's a very important topic that we had a conference in last year. What was the Chinese name of the conference?
Oh, that's very difficult. That's too difficult.
Okay, but last year the conference that was here was about configural processes, and the idea is that you can take parts of objects and you can put them together in a way that is either like this or like that. Now, think about my hands. When they're like this, nothing special happens. But when my hand falls this, there's suddenly a circle here. It turns out that the visual system is very sensitive to circles, to closed forms. So we measured capacity for those kinds of triangles and circles and so on. It's an interesting study, but I will skip this now. And talk a little bit about the application of the technique to cognitive aging. So, Andrew mentioned that older adults tend to be slower than younger adults. And Shulan Poster actually tries to look at the explanation behind this. Why is it that older people are slower than the younger? One potential explanation is that their visual system perhaps is impaired. Another potential explanation is that the entire processing is slower. Another potential explanation is that they are simply more cautious. They are taking their time to make a correct decision, and there was a very interesting graph that Andrew had showed us. It was something like this, where the this is accuracy, and that is speed. And you can see that there is only a very small difference in the accuracy, and a very big difference in speed, and that's why response time models